All right, hey guys. Um, where am I? This is number 5, which I was going through in the last video, and I made a mistake. I'm going to kind of just show you. Um, so we had done the whole process. We've gotten to our optimization equation. We differentiated, getting this pink thing up here at the top, and from there we split it. We pulled out the numerator in green, and we found 3 roots. We got 0, and we got plus or minus root 6 over 2. Then I pulled out the denominator in yellow, and we got to this fourth power function, which I tried to factor like a quadratic. And that's where I made a mistake, because I've got minus 4 and plus 1. That doesn't make positive 4, that makes negative 4. So this ain't happening. All that stuff is bad. So I cut that out, and we're starting kind of again. I think I talked about this problem in class with a bunch of you guys. I think we did it in period 4 and period 6, but maybe not in period 1. But anyway, if you look at this quadratic, well, it's not a quadratic, but it's like a quadratic. But if we kind of ran this through the quadratic formula using these coefficients, we'd see that it doesn't have any real roots. Or if you just graph this again, you'll see it doesn't have any real roots. This would be a quartic function that's always up above the x-axis. So this guy has no real roots. So it doesn't generate for us any new critical values, which means if we go to test the 3 critical values that we found before, then we should be good to go. So I'm going to get rid of this whole number line because this was a mistake. And so this 2 and negative 2 are not actually critical values. We would just want to test these 3. And if you test those 3, then we can figure out who's going to generate our max and min. So here's a 0, here's a negative root 6 over 2, here's a positive root 6 over 2. I think someone told me in class that root 6 over 2 is like 1.22. And so taking that as our value, we know that on this interval we just have to be less than negative 1.22. So I don't know, something like negative 10 is great. Between here and here we have to fall between negative 1.22 and 0. So negative 1 is really the only candidate that's an integer for us. And over here we'll use positive 1. And then I just have to be bigger than 1.22. So I don't know, 5, 6, 7. I'm going to go with 10. But we're going to test this in our derivative. And our derivative was, this was our numerator, right? And you could factor a 2 out of this as well. So really we've got a factor of 2x and 2x squared minus 3. And then our denominator was 2 times the square root of x to the 4th minus 3x squared plus 4. So as we substitute in, plugging in negative 10 gives me a negative, and then negative 10 squared is positive 100, so that's going to come out to be positive. Then downstairs you've got a 2, which really doesn't matter for us. But if I plug in negative 10, the negative 10 to the 4th will come out positive and really big. Then negative 10 squared will be positive, but not that big. So if I subtract it from this big boy, I'll still be positive. And if I add 4, I'll still be positive. So we can see that the derivative is negative. So in this whole interval, we've got a negative derivative. And then if I plug in negative 1, I get negative 2, so that's still negative. Here when I plug in negative, I get 2 minus 3, so that's still negative. And in the denominator, what do we get at negative 1? We get positive 1 minus 3 times positive 1 plus 4. That's negative 2 plus 4 is a positive. So this all comes out positive. Then if we test positive 1, then we get a positive and a negative all over a positive. So we're back to negative. And if we test positive 10, we get a positive, and a positive. So we're positive. So what all this means is kind of what I hope we expected, which is that this guy is for sure a min, because the derivative goes from negative to positive, meaning the graph goes from decreasing to increasing. That gives us a min at this x value. But the critical value that we found at 0 is not a min, it's a relative max. because we go from increasing to decreasing there. So the value at 0 gives us a relative max, but then we decrease again and increase again. So the critical value at root 6 over 2 is another min. So, all right, I don't know if you're tuning in straight from the other video, but if you've lost track of what the heck we're even doing anyway, we're trying to find the points on the graph of this function that are closest to 0, 2. So again, 4 minus x squared is a graph 1, 2, 3, 4 with its vertex at 4, and it's a downward opening parabola. I guess I already drew it over here, but whatever. Then you've got the point 0, 2, and basically we're saying that the 2 points closest to it are these 2 points here and here. And so we just decided that those are the points with the coordinates root 6 over 2 and negative root 6 over 2 as their x coordinates. And to find the y coordinates, you just plug into this equation. So if x or if y is 4 minus x squared, then y is 4 minus root 6 over 2 squared. So that's a 4 minus a 6 over a 4, which is a 4 minus 3 over 2, which is an 8 over 2, minus a 3 over 2, which is a 5 over 2. And you'll get the same answer if you plug in negative root 6 over 2, because we're going to square it, it's going to turn out positive. Or just looking at the picture, you can see that both of these points should have the same y coordinate, because they're reflected images over the y-axis. So the x's should be opposites, but the y should be the same. So 5 halves and 5 halves. And this question is now done, because these are the two ordered pairs that are the minimal distance away from the point 0, 2. So that's 5, all done. So let's go to 6. 6 says a rectangular page is to contain 24 square inches of print. The margins at the top and bottom of the page are 1.5 inches, and the margins on the left and right are 1 inch. What should the dimensions of the page be so that the least amount of paper is used? All right, so a rectangular page is to contain 24 square inches of print. So that means we need 24 square inches on a piece of paper. But that's not the piece of paper. That's just the piece, that's the area that we can actually print in. So what they're saying is if we go up and down by 1.5 inches, and that creates margins up above, right? And then we go left and right by only 1 inch, and that creates margins over here. So the idea is that really what you've got is this big old piece of paper here that has margins. But the area on the paper that you can actually print on is that area there. Boop. And that's supposed to be 24. So if I were doing this problem, and I am, I would label the printed area as x and y. So those dimensions are going to be x and y. But what I want to actually be solving for are the dimensions out here, the outer dimensions. But I want the inner dimensions to be x and y, because what's going to happen is this dimension of the paper can now just be x plus the margins. If we let the paper be x, then the inside printable area would have to be x minus the margins, and that's fine. You could do that, but I don't feel like dealing with negatives, and I feel like you probably don't either. So by labeling this printable area as x and y, then I can let this outer dimension be, let's see, weren't the margins on the left and right 1 inch? So this is 1 inch, this is another inch, so the total width is x plus 2. And then by the same token, the total height of the piece of paper would have to be y plus, now this is not 1, it's 1.5, so it would be y plus 1.5 plus 1.5, aka 3. So there's kind of the initial setup of the problem, is you've got a piece of paper that's x plus 2 by x plus 3, and the inner area is x by y, and then our constraint equation would have to do with the fact that that printable area has to be 24 square inches. So we can say that our constraint is x times y has to be 24. And the equation that we want to optimize is the area of the piece of paper, because we want to use the least amount of paper. So the area of the piece of paper, well, area is still just length times width, but we're going to use, instead of x, y, those inner dimensions, we got to use the outer dimensions. So the x plus 2 and the y plus 3. And when we say optimize here, we're trying to minimize rather than maximize. Minimize? That's a lot of I's. Minimize. Okay, whatever. All right. Again, we're now at that point where we've got a lovely equation, but it's got too many variables in it, x and y. But that's where our constraint comes in. We can either divide by y to solve for x, or we can divide by x to solve for y. And you guys typically like to keep equations in terms of x, so that means solving for y. So divide both sides by x, and you get a y that equals 24 over x. You can now take that expression and plug it in. So my optimization equation now is that the area equals x plus 2, and then instead of y plus 3, we'll drop in the 24 over x. Okay, now you've got an equation, and it's only in terms of one variable. It's not in the best position for differentiating, so if I were you, I would FOIL this out. And so we'll go a times 24, we'll go x times 24 over x, and the x's will cancel, just giving 24. If you do your outer product, you get a plain old 3x. Your inner product gives you a 48 over x. And then last times last gives you a plus 6. So there's the four terms you get when you FOIL, FOIL. And this is still not great. The 24 and the 6 can be combined. If we're going to go in descending order, then of course the 3x comes first. Then the 30 goes in the middle. And this guy actually comes last, because this guy is technically a 48 times x to the negative 1. So that negative 1 power is less than no x's. So this is technically descending order. But this is also the form I'd want it in, and I can now take my derivative. So I don't know, let's switch over to white for that, why not? So we get a prime. We are now finally differentiating, and we get 3. And the derivative of 30, don't forget, is just 0, because that's a constant. Then we get minus a 48 times x to the negative 2. That's it. That's the derivative. Now just clean this up and get it into a better form so that we can set it equal to 0 and solve. So obviously the 3 stays 3, 0 just goes away. This will now be a minus 48 over x squared equals 0. And we could solve this a couple of ways, but the way that you're technically supposed to solve is to generate a common denominator. So multiply by x squared over x squared. Then you can combine these terms. And in the numerator, you can even factor out a 3. So you'd end up with 3 times an x squared minus a 48. And then this is all over an x that is squared. And it's all supposed to still equal 0. Then from here you could factor. So the numerator is a difference of square. Oops, screwed that up. That's a 16, of course, when you divide by 3. Which makes that a difference of squares. So you can factor that down to an x plus 4 and an x minus 4. And downstairs you've just got the x squared. And if all this is supposed to equal 0, if we're looking for critical values, then the zeros are the plus 4 and minus 4. But there's also a critical value at 0, because that's where the derivative is undefined. So technically, I would want to test all 3 of those values and see who works. But technically, we should be thinking about the context of the problem. Don't forget, we're talking about a piece of paper here. And I'm pretty sure that this x dimension, it certainly can't be negative, and it can't be 0 either. So actually, out of all these 3 critical values that we found, negative 4 is extraneous because you can't have a negative dimension, and 0 is extraneous too because you can't have 0. So really the only critical value we've got is 4, And technically you are still supposed to run a quick sign test to make sure that 4 is actually giving us a minimum value. So here's 4, but don't forget that 0 is also a critical value, so the sign of our derivative may change to the left of 0. Same thing with -4. So I'm going to draw all of the intervals here, but the only intervals that really matter are the ones to the left and right of 4. But make sure you stay within those intervals, right? Don't go to the left of 0 or you're in the wrong interval. So again, these are the intervals I care about. And so I'll test whatever, any number from in here. I don't know, we'll test 1 and we'll test 10. And where are we testing? Right in here, in the derivative. And the 3 is kind of irrelevant because it's positive, so it doesn't do anything, so whatever. But if I plug in 1, I get a positive, a negative, a positive. So we are negative. If I plug in 10, I get a positive, a positive, a positive, so we're positive. And this again is what we hoped to see, because I see that the function is decreasing, then it's increasing. That means that the extrema we get when x is 4 is truly a min like we wanted it to be. Now, where were we on this? We were talking about a piece of paper, right? And in that piece of paper was a printable area, right? And the printable area was x by y. But the answer to the question is the dimensions of the full piece of paper. So let's walk through this now. What do we know? We just found out that x is 4. So that's 4. Great. Well, if x is 4, what's y? Well, remember the printable area was supposed to be 24. So if x times y is 24, and we just figured out that x is 4, then I'm pretty sure y is 24 divided by 4, so y is 6. Which is still not the right value. We're looking for the values of these dimensions. So don't forget, this dimension was x plus 2, and 4 plus 2 says that that outer dimension of our piece of paper wants to be 6. And the vertical dimension was y plus 3. And if y is 6, then 6 plus 3 says this dimension should be 9. So our final answer here should be that the paper should be 6 inches by 9 inches. That's it. Another problem down. Okay. So 7, we're creating an open-topped box with a piece of cardboard, and we're doing it again by cutting squares out of the corners. So we've done a problem like this before. So again, if you're just kind of watching, I would encourage you not to watch. If you haven't tried this problem yet, please try it. There will almost certainly be one like this on the quiz, and I think I've done 2 examples like this already. So if you've not done this, again, like pause the video and try it yourself first. Look over the old ones, you know, give yourself an opportunity to do this before I spoil it for you. All right, that was fair warning. Okay, I'm going to do it now. So this is another question about a piece of paper, or a piece of cardboard in this case, but this one happens to be 16 by 30. And again, the plan is to cut little squares out of the sides. So you go cut, 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 and cut and cut. And then you fold along these edges. And then what you do is you let this becomes essentially the bottom, because you're going to fold up these sides. So here's the sort of bottom of what's going to be a box. And then these sides flip up. So you go flip up, and that becomes a wall. And then this other side folds up, fold up, fold up. That becomes a wall. And then this side folds up, yoink, and this side folds up, yoink. And the next thing you know, you got yourself a shallow little box, right? And the floor of that box is like this blue face here. So boop, whoops, I'm not going to try to do that again. All right, but that's it. So the question is, how did these dimensions from the cardboard become the dimensions of this box? So the paper started out at 30 dimensions, or yikes, it started out at 30 inches wide. But we cut out a square that I presume we're all going to call x by x by x by x. But there's a second square over here that's x by x by x by x. Now 30 goes all the way across. And I'm not interested in that dimension. I'm interested in what's left over after I cut away the squares. So wouldn't that be 30? Take away x, but then take away another x? So it's 30 minus 2x. And this dimension here in pink is this dimension right here. It's this front edge of the box that we formed by folding. So this dimension is 30 minus 2x. Then this dimension that used to be 16, that went all the way up and down. Well, again, we're cutting a square from both sides, so 2x's get taken away. So this dimension here is 16 minus 2x. And that dimension there corresponds to essentially this edge here. So that's 16 minus 2x. And then finally, sort of tricky, but this edge here for the square, the x by x thing, these two bits come together now and are at a height of x. So that x from the square is where these sides meet up and form the height of the box. But that's it. You've got this three-dimensional box now whose dimensions are 30 by 2x, or 30 minus 2x by 16 minus 2x by x. And this problem is about getting to the largest possible volume. So that means the equation we want to optimize is our volume equation. And volume is length times width times height. So it should just be 30 minus 2x times 16 minus 2x times x. And that's our volume. And I would go ahead and expand this out before trying to differentiate. So let's FOIL these two binomials. Getting, 30 times 16, that's going to be 480. So that's the first. Then the outers are negative 60x. The inners are negative 32x. And the last times the last is plus 4x squared. And then don't forget you still have an x. So now we'll distribute the x through, and this little quadratic will turn into a cubic. And again, killing two birds with one stone. I'll pull the 4x squared to the front. It'll now be a 4x cubed. I'll combine these terms in the middle. That's 92x times x is 92x squared. And then plus 480x. And that's still just the volume equation. And we know that to find the maximum value, we'd want to find the derivative. So let's differentiate. Getting 12x squared minus 184x plus 480. And we want to go ahead and set that equal to 0 and start solving. And right away I see I can divide by something. I can certainly divide all my coefficients by 2. And then I'd have what, 6 and 92 and 240, and so I could divide by 2 again, which means I can just divide by 4. I think 4 is the best we can do. So if I divide through by 4, then we land on a version of our derivative where v prime is 3x squared minus 46x plus 120, and that still equals 0. Alright, so now we got to try to factor that thing, and it already looks like it's going to be pretty tough because 3 times 120 is 360. Oops. And that number's got kind of a lot of possible factors, so we better try to be organized here. Pretty clearly 1 in 360 isn't doing it, and 2 in 180 isn't really any better. 3 in 120, still pretty far off from 60, right? I still might recommend you just keep going like this though in a methodical way, because eventually you'll get there. So 4 and 90, okay, getting a little better. 5 and 72, I think that's right, 5 and 72. 6 and 60. 7 mercifully is a number that doesn't go in, but 8 does. 8 and 45. Uh-oh. 8 and 45. All right, did I like miss it? 46? No, I missed it. All right, 9 and 40. Okay, that ain't it. 10 and 30. Okay, that was actually pretty obvious now. All right, 10 and 36 is clearly the pair. And we'd want to let both of them be negative, because then we would get a negative sum and a positive product at the end. So, okay, that wasn't so bad after all. So v prime is going to be, let's see, there's going to be a 3x and there's going to be a 1x. It's all still going to equal 0. And again, I've got a 36, so that means if I already have a factor of 3, I'll plop a negative 12 here, so that my outer product is negative 36. Then if you want a negative 10, you'll plop a negative 10 right there, and that'll do it. This is now my factored form, and I can see that my my roots, my zeros are, if I add 10 and divide by 3, positive 10 thirds, and also 12. All right, hey, real quick, do you guys remember that the dimensions of the piece of paper were 16 by 30? Doesn't that mean we have kind of an implied domain where there's just no way that we could cut a square that was 8 inches or more, right? We need to be smaller than 8 because, well, this side's only 16. So if we tried to cut squares that were 8 and 8, you'd be cutting all the way across the paper and you'd just have nothing left. So this 12 has got to go, because we've got this sort of naturally restricted domain that says the length of side of our squares has got to be less than 8. 12 doesn't fit that bill. 12 is bigger than 8, so 12 is extraneous. But our 10 thirds looks promising, so promising that I might even test it on a number line. And again, if you plop down 10 thirds, don't forget to also plop down the 12. Because again, the only intervals we're interested in are the interval to the left of 10 thirds and the interval to the right of 10 thirds, but stopping at 12, because after 12 the sign of our derivative will change. So I want to stick to this, which means in this interval I could test 0. 0 is a great candidate. 10 thirds is only like 3-ish, so 10 is good here. So 0 and 10 are both easy to evaluate. And the whole derivative is easy to evaluate once we're factored. We can see that plugging in 0 gives a negative and a negative. So in this interval we're positive, which is good. We expected that. We're trying to go from positive to negative to show that 10 thirds is going to be a max. Plugging in 10 gives a positive and a positive, which is good. Just kidding. We were expecting a negative, because we weren't trying to go from increasing to decreasing. So 10 gives a positive and a negative, which gives a negative, which is great. That's what we wanted. So we can say, therefore, V has a max when X equals 10 thirds. All right, but whatever. We did our sign test. That happened. Now, what are we actually doing? We're trying to find just the side of the square. Is that all they asked for? What size of square should be cut? Yeah, that's all they asked for. So we're actually done. Just x equals 10 thirds is the answer. You'd say side of square should be 10 thirds inches. I assume it's inches. I think everything's been inches, just in case. Yeah, it's inches. All right. So that's all well and good. Just remember that on the quiz, I'll probably ask you to go a little farther. I'll probably ask you, hey, what are the dimensions of the box that results? And what is its maximum volume? So given that the dimensions of the box, if you scroll back up, you got the dimensions right here. So the height would obviously, let's keep it in length width height order. Height's the easiest one. The height is 10 thirds. That's what we solve for. The length would be 30 minus 2 times 10 thirds. So that's 30 minus 2 times 10 thirds is 20 thirds. But 30 is 90 thirds, so that's 70 thirds. And 16 minus 2x would be what? 16 minus 20 thirds? And 16 is 48 thirds. So that's 28 thirds. So if I asked you to actually give the dimensions of the box that had the maximum volume, you'd want to tell me it's 70 thirds by 28 thirds by 10 thirds of an inch. Don't forget the units. If I asked you for the volume, you'd have to multiply all that stuff together, and you'd get some big number in the numerator. Your denominator would be what, 27? Numerator would be whatever. But the volume would be cubic inches, of course. So just remember, I may ask you to go a little further than what we're doing here. They just wanted the lengths of the sides of the square, but I'd probably ask you to give the dimensions of the box and the volume of the box. Okay, moving on to 8. Rectangular pig pen. All right, this one's cool. Next one is, well, all right. So if you can't imagine what they're saying, imagine you're looking straight down, and this guy's already got like his barn, right? So here's his little barn, barn. You know, Cheryl. Well, there's a perfectly good wall here already on his barn, right? So he doesn't have to put 4 walls of fence. He can just build out from the wall and go build. And then the next thing you know, he's got himself a nicely enclosed pen for his animals. It only needs 3 walls because he can build it right up against his little barn, right? Put a chimney on the barn so it doesn't get cold. Here, have a chimney. Maybe a little smoke. Okay, anyway, you get it. Maybe you do. I don't know. But what's the deal? It says he's got 300 feet of fencing. Fencing goes around the outside of a shape, doesn't it? So that sounds a lot more like perimeter than area, doesn't it? And if this thing is rectangular, then if we call this dimension x, then the opposite side would also be x because we're a rectangle. But it doesn't say that we're trying to make like a square. So that third side should not necessarily be x. That third side can be anything at once. So call it y. Now, if we're going to use all the fencing, right, we want to maximize the area. The only way to maximize area is to use all the fencing. So we would want our x plus y to be 300. And that's our constraint equation. And maybe it dawns on you, and maybe you never even wrote the y. Maybe it's clear to you that obviously if I have 300 feet, then this dimension has to be whatever's left over when I'm done using these 2 x's. This dimension's going to be 300 minus 2x. And that bears out. X plus x is 2x, right? And so if we were going to actually use a constraint equation, we'd be solving for y, and it would prove to be 300 minus 2x. If you can kind of logic that out in your head, I don't need you to write out, this is the constraint equation, and jump through all those hoops. Like, some of these constraints should be kind of obvious, and if you can do that, then great, do that. I don't need to see this thing called a constraint equation. Now, I do need to see the equation we're optimizing, and we're trying to optimize area. And based on the constraints and what we talked about, the area would be x times 300 minus 2x. And then from here, I mean, solving this guy's pretty easy because we'll distribute the x for sure, getting 300x minus 2x squared. But we just want the derivative now, and this is a very simple derivative. It's just product rule. It's power rule. So you just get 300 minus 4x. And you set that equal to 0. There's only one root, so you add 4x to both sides, you get 300 equals 4x. You divide by 4, getting 75. That's our only answer. Even though it's our only answer, we're technically still kind of expected to run a quick sign check to make sure that it's actually a max and not a min. If it was a min, then maybe our maximum values would come at the endpoints of our natural domain, but that doesn't typically happen. So all right, 75. So I can plug in 0, I can plug in 100, just run a quick test. If I plug in 0, I'm positive. If I plug in 100, I'm negative. So guess what? If we're positive and then we're negative, then we are expecting a maximum value at 75, just like we thought. So that's great. And the answer to the question is, what dimension should the farmer use to construct the pen with the largest possible area? Here, we talked about this a bit, but we said, what did we say? 75. And the other dimension is what? 300 minus 75 doubled, which is 150. And 300 minus 150 is 150. So if you just said 75 by 150, does order matter here? It kind of does. Because if you said 75 by 150, I don't know which way you mean that. Do you mean there should be 250 feet sides and only one 75-foot side? Well, that violates our constraint, obviously. The 150 and 150 would make 300, then you wouldn't have 75 left over. But you better be a little more careful here. I think on the answer key I actually wrote out the two short sides. Are 75. The longer side is 150. Just something that makes it clear that the three walls should be 75, 75, and 150, rather than 150, 150, and 75. But both of these are feet, by the way. I have to say that. We must say that. But that's the end of this problem. It's not so bad, in my humble opinion. Let's do 9, or let's skip 9. I know there's one coming up that we skip. Alright, this is not the one we skip, but I did say in class to some of y'all that I really don't think I'll ask about a cylinder because we haven't really gone over it in a while, and I don't feel like it. But I'm going to do it so that those of you who, like to learn and stuff can at least see it. So it says, what's the radius of a cylindrical soda can with volume 512 cubic inches that we use the minimum material? Minimum material would mean minimizing the surface area. So this guy then is the guy we want to try to minimize. And the volume is our constraint. It says we want to have a volume of 512 cubic inches. So my constraint equation then would be that 512 equals pi r squared h. And we're trying to optimize our surface area, and surface area is apparently 2 pi r squared plus 2 pi r h. Okay, why is it this, by the way? Well, think about what a cylinder is. A cylinder is two circles. That's the 2 pi r squared. Literally, pi r squared is one of those circles, but the circles are congruent, so you double it. That's what that first term is. It's the two circles. Now, if you've ever unwrapped a toilet paper roll or whatever, then you know it kind of unwraps into a cylinder, right? And the base of the cylinder would be the circumference of the circle. So this base is circumference, which circumference is 2 pi r. Now the height of this is h. It's the height of the cylinder. So that's what this term on the end is. It's literally the area of a rectangle whose base is the circumference, 2 pi r, and whose height is the height of the cylinder. I don't know that anyone cares, and you don't need to know that, but that's why the formula for the surface area of a cylinder is this. Okay, now, I don't know, that's it. I mean, here's my equation to optimize. I am noticing I've got an r here and an r here and an h, and that's not great. We want to only have one variable. Since there's an r squared and an r, I should probably work towards just replacing h, which means hitting up my constraint equation and solving for h by dividing by pi r squared. And we find, cancel, cancel, that h is equal to 512 over pi r squared. So I can plug that in now. My optimization equation is now a equals 2 pi r squared plus 2 pi r, and now instead of h, I substitute in this expression, the 512 over pi r squared. All right, and now I'm going to want the derivative of this, so I'm going to want to clean up first. So we get a equals 2 pi r squared plus, let's see, this is all over 1, right? So I can't help but thinking that these pi's cancel, and I can't help but thinking that this r cancels one of these r's. And so what I'm looking at now is 1024 in the numerator, because I take the 512 and I double it. all over just one r down there in the denominator. So again, I'll clean this up a bit. We'll say that a is equal to 2 pi r squared. But this is going to be 1024 times r to the negative 1. So that means I'm ready to differentiate, and I get an a prime. That equals, let's see, multiply by 2, so you get 4 pi as your new coefficient. And then r's exponent goes down by 1, so it's only to the 1, so it's 4 pi r. Then it'll be minus 1024 r squared, or r to the negative 2, sorry. Okay, so you're going to now set this equal to 0 and try to find those critical values. And again, if this is 4 pi r, I'm going to kick this r down to the denominator. Just get my 1024 over r squared. And again, I don't want to miss any solutions, so I need a common factor of r squared. So I'd have to multiply by r squared over r squared, which brings this guy up to cubed. I already had an r. So if I multiply by r squared over r squared, then my numerator is r cubed, my denominator is r squared. So that gets me a 4 pi r cubed minus 1024 over r squared, which equals 0. And again, I would want to grab this numerator, set that equal to 0, and see what solutions it brings. Then I'd want to grab my denominator, set that equal to 0, see what solutions it brings. And we'll start with the easy one. R squared equals 0 when r is 0. So technically that's a critical value. That's a point that I want to consider. Then 4 pi r cubed minus 1024 equals 0. I guess we're adding 1024. And then I guess we would divide by 4. So we're landing there. Oh, I did math behind my face again. Oh well. Sorry. Oh, I didn't really do math. I told you guys that r squared equals 0. The only solution was 0. You probably didn't need to see me do that. Alright, but now I've got this pi r cubed. That equals, geez, let's see. If I divide by 2, it's 512. If I divide by 2 again, it's 2... I don't know. I'm bad at math. 512 divided by 2. What is that? 250 plus an extra 6, so 256? Okay, yeah, that makes sense. Alright, 256. But guess what? I got to move the pi too. So really when we divided by 4, we should have just divided by 4 pi. I'm going to do that in 2 steps though, just to maybe keep it feeling a little bit clean. So that pi is gone. Now I take the cube root and I get r equals the cube root of 256 over pi. Can this be cleaned up? I don't know. What are the factors of 256? I know that's a power of 2, right? 256? Well, let's find out. 256, 2, 1, 28, 2, 64, 2, and 32. Alright, and 32 finally, I remember the 32 is 2 to the 5th. So here's 5 2's, 6, 7, 8. 256 is 8 2's. Why do I care? Why do you care? You probably don't. But here's why you might care. Because that means in the numerator, the 256 can be 2 to the 8th, but 2 to the 8th is a 2 to the 3, and then another 2 to the 3, and then another 2 to the 2. Hopefully you guys agree that 3 plus 3 plus 2 makes 8. Why am I breaking it down like this though? Good question, fair question. It might be because those are now perfect cubes, which I hid behind my face. Boop, boop, boop. Okay, so those guys are perfect cubes now. So if I take the cube root of 2 cubed, that's plain old normal 2. And if I take the cube root of this 2 cubed, that's plain old normal 2. And if I take the cube root of 2 squared, that's going to stay a cube root, and it's going to stay the cube root of 4. and that's all over the cube root of pi. But I thought we didn't like radicals in the denominator, and we don't. So what would you multiply this by? Well, you would want the cube root of pi cubed, so you'd have to multiply this by an extra factor of the cube root of pi squared. That would give you 3 pi's that you could then take the cube root of, but you'd have to do that to the top as well. And you guys are probably hating me right now, but that's okay, because I know I'm doing some good math over here. God, I can't keep it on the screen though. Alright, you go here. That's what I'm doing. So where the heck are we? I think 2 times 2 is 4. That's easy enough. So I'm getting a 4 times the cube root of 4x squared. I mean 4 pi squared. And that's all over plain old normal pi, because this will be the cube root of pi cubed, which is plain old normal pi. So hey, we did it. Remember, I've been trying to get you guys to give me exact answers for forever? That's the exact answer. Now what, pray tell, is this approximately? I have no idea. So let's figure it out together. Alright, here's my trusty calculator. So 4. Oh, cube root. Alright, whatever. Some of you guys know that to find the cube root you can go into math. And then just down to cube root, option 4. So I'm doing 4 times the cube root of 4 pi squared, close parentheses. Let's just see what that is. It's that. Then you divide that by pi, and it's that. So I'm getting 4.335 as an approximated value here. And for all of you wondering, yeah, you're right, this kind of was a waste of time, because you probably could have just left it in its original form. Its original form just being the cube root of 256 over pi. I'm kind of a stickler for simplifying though. I'm kind of a stickler for cleaning up denominators. But just to prove it to y'all that these are the same after all, what is this guy? Just the cube root of 256 over pi. So if you just plug that into your calculator, by the way, the other way to do a cube root is just to go 256 over pi and just raise it to the power of 1/3. Remember that square roots are, oh, but this needs to be in parentheses though, I do believe. But just like 1/2 is a square root, 1/3 is a cube root. So just, oops, I'm screwing up again. It's getting late. Second insert, division. Yes, 256 over pi, cube root of that. It's going to be the same number unless I screwed something up, but no, it's the same number. So if you guys gave me the cube root of 256 over pi, I don't think I'd throw a hissy fit. I think I would be okay with it. But it would really be lovely if, you know, when you graduated high school, you knew how to simplify cube roots and you knew how to rationalize denominators. And if you do all that, then technically your answer should be this one, that one there. And technically this one is not so good. So whatever, moving on. I think we're moving on. Probably not moving on. What the heck was going on here? Oh right, we were trying to find the radius of a cylindrical soda can. And since all they wanted was the radius, then yes, we are done. This is the answer. You'd want to make the radius about 4.335. Moving on. Power stations on the side of a river. Okay, I told you guys you could kind of skip this one because I don't really care about money problems, which is a bad thing because these money problems are, guess what? Applications. And this class is supposed to be called calculus with applications. But I just don't, I don't know, I don't really like these problems, so I don't care. How's about we set it up? If anyone cares, we'll set it up. It says a power station is on one side of a river that's 1/2 mile wide. So draw yourself a river. And this distance is 1/2 mile. Okay. And a factory is 6 miles downstream on the other side. So there's a power station on one side, power station. Then there's another power station, and the distance between them is 6 miles. Yeah, so this is not drawn to scale at all, but that's okay. This is 6 miles. Downstream on the other side, it costs 60,000 per mile to run power lines over land, 85,000 per mile to run them underwater. Find the most economical path for the transmission line from the power station to the factory. Hint: total cost equals on land cost, distance on land. Yeah, I know that. We all know that. Alright, so what are you getting at here? I don't know if I know how to do this one, really. Probably not worth our time even to think about. Let's blow this up. If you guys want to fast forward, just fast forward, because I'm probably about to ramble for a few minutes. But blowing this up, hopefully you understand the idea, is I want to connect these two factories. Hopefully you understand that just building a line straight from here to here, probably not the best solution, because that would be entirely underwater, and you're paying the 85,000 per mile the whole time. You'd want to take advantage of the 60,000, right? So what does that mean? Does that mean I should take a path that goes as far as it can on land, right? If I just go as far as I can on land and then suddenly cut across, then that certainly makes my trip across the water the shortest it could possibly be, right? And so that intuitively to me sounds like the best deal, but this path is now overall longer than a path that maybe cuts down a bit and then diagonally comes across and then comes down. Maybe that path is shorter than the green path because it takes at least a bit of a shortcut. So like where's the optimal point, right? So going straight across is the shortest possible trip, but it's the most expensive path. Green is sort of the longest possible trip, but it takes good advantage of this cheaper overland power lines. So I don't know. How do we model this? I couldn't begin to imagine, and I don't want to. I guess the yellow is sort of the most generic path because it has some on land and some of the other. So maybe we could say that this land distance is x. Let me take these away. Let's kind of make the yellow more obvious. If I came on land for a bit and then cut across the water, then that's kind of the optimal thing. And that's the same as doing some land and some water and then some land again. So let's just say the land trip is going to be x. And if that's x, then what's this across the water bit? And the answer is, of course, build yourself a right triangle. Because if this first bit is x, then this next bit would be 6 minus x. And of course, this distance across is a half a mile. So we've got the two legs of a right triangle. So we could model this diagonal as the hypotenuse of a right triangle. And it would end up being the square root of the vertical edge, 6 minus x squared, plus 1/2 squared. And that's just Pythagorean theorem, if you're with me. You would take this leg, square it, you'd take this leg, square it, and you'd add them up. And that would equal this distance squared. So if you take the square root, then that's that. But it sounds to me like that's going to be our equation. So our cost would be the x miles that we want to do on land at a cost of 60,000 per mile, which we can just say 60 and then know that everything's in thousands. Then we could add to that this whole big blob. So the square root of 6 minus x squared plus a half squared, which is just a quarter. I'll go ahead and just say a quarter. I wish my thing didn't do that with 4s. All right, a quarter. And that's getting multiplied by the underwater fee of 85,000. But that's it. This is now the equation that we would want to differentiate. I'm not going to do that. That much I'm not going to do. But hopefully this setup kind of made sense and helps you to think through this process. But honestly, no. There's no way I'm going to give you a question like this. So moving on. what? 10. 10 again. Now 11. Okay, this rancher problem is fair game in my humble opinion. It's kind of like the one from before. I don't remember if your paper had the diagram on it. I don't think it did, so I'm going to throw this in the trash and make you think about it yourself. But it says a rancher has 200 feet of fencing. Now we did a problem a second ago where the rancher built his corral up against a wall. So he already had a big old wall, which meant he could build a corral using only 3 walls. And we did that. This question is very different, but at least it has that same idea of perimeter, because I've got 200 feet of fencing I can use. So that's going to be the perimeter of whatever structure I make. Now it says we want 2 adjacent rectangular corrals. So adjacent means they're right next to each other. What it doesn't say is that the corrals are supposed to be congruent. We do kind of have to assume that they're trying to be congruent, because if you had a rectangular corral and then a completely different rectangular corral, we would end up with way too many variables. And if you stuck these together, then those are adjacent corrals, but they're not congruent. And so suddenly you'd have to have dimensions of, like, this guy's A by B, but this one's C by D. And there's no way you could resolve all those variables down to just one variable. So it doesn't say, which I guess is why it says see the figure. The figure was there, I guess, to show you that. So I'll bring the figure back. Blindingly bright. Sorry. So yeah, they wanted us to go ahead and assume that the 2 corrals were congruent, because as soon as we assume they're congruent, we just have x for this one, x for this one, then of course x up here, because opposite sides are congruent, x here. Then the vertical dimension is y, and then you just run one down the middle, so there's a third y. That means our constraint equation, our 200 feet of fencing, would have to equal 1, 2, 3, 4 x's added together plus 3 y's added together. There's your constraint equation. And we want to maximize area, and hopefully you guys are catching on now that area is just going to be length times width, so it would be xy, but then there's 2 of them. So it's an area of xy doubled. So your area equation is really simple, other than the fact that it has 2 variables in it, which we can't really do. So we better take our constraint equation and solve for either x or y. And again, it seems to be everybody's preference to solve for y so that we can replace y and keep x. So solving for y gives 200 minus 4x all over 3, which means my area equation becomes 2x times this whole thing. 200 minus 4x. Now whatever. All over 3. And then there's not a ton I can do with this. I'll go ahead and distribute, I guess. Yeah. And in the interest of cleaning this up, I suppose I'd just pull the 3 out and just make a coefficient of 2/3. Maybe I do this? I don't know. Then I distribute the x, getting 200 x minus 4 x squared. That good? I guess I want to distribute the 2/3. Sure, let's just distribute it. So you'd have essentially a coefficient of 400 on an x, and you'd have a coefficient of 8. Plain old 8. 8/3 on an x squared. And now we can differentiate that, getting an a, getting an a prime that equals, well, 400 minus 16/3 times x, and we want that to equal 0. And this is a linear equation, so we should only get one solution. That solution is going to be kind of ugly, but it's going to be 400 equals, I would just add the other guy to the other side, so it equals 16/3 times x. And again, the easiest way to clean this up would be not to divide by 16/3, but to multiply by its reciprocal. So multiply by 3/16. Because if you multiply by 3/16, you'll watch as the 16s cancel, the 3's cancel, and you now have an isolated x. And over here, the 3's cancel, and I can cross-reduce these guys. So what is this? 200 and an 8, and then 100 and a 4. So 50 and a 2, so 25. It actually comes out cleanly. Thought it was going to come out ugly, but it didn't. Alright, so 25 should be the answer. This is annoying, I know. You just want to be done and celebrate, but technically you're supposed to run a first derivative check. Let's make sure that 25 is actually giving us the maximum that we're after. And we're testing it where? In our derivative, right? So this white equation right here will do just fine. And plugging in a number less than 25, let's do 0. Plugging in a number greater than 25, I don't know, 100. But plugging in 0 gives 400 thirds minus 0. That's a positive. Plugging in 100 gives 400 thirds minus 1600 thirds. That's a negative. So yes, therefore, max at 25. There, sign test done. So that means what? That means x is 25. So what's y though? Because I'm pretty sure we had to find the dimensions of the corrals. But again, we've got our handy dandy constraint equation right here. So if you want to find y, just plug in the 25 that you found, and you get 200 minus 4 times 25, all divided by 3, aka 200 minus 100, all divided by 3, which is 100 thirds. Okay, so that's y. That means what dimension should be used so that the enclosed area is a maximum? Again, I want to word this just right, because if we just said 25 by 100 thirds, then which dimension is which? Which dimension is which here does matter, right? So I think the way I framed it on the answer key was to say that the shared wall should be 100 thirds, and then that made it clear which dimension was which, right? So the wall that they share should be 100 thirds. So the answer here should be he should make 2 congruent 25 by 100 thirds corrals that share a 100 third, what are these, feet? These are all feet, right? So feet that share a 100 thirds foot wall. Because if you shared the 25-foot wall, if we stuck these together differently, does that matter? Now I'm not so sure. I think, oh yeah, because if we stuck them together differently, then suddenly you'd have 3 x's and 4 y's, which would not work with our 200-foot constraint. So we do kind of have to stipulate that bit to make our answer completely valid. Oh, what did I just write, and where did I write it? Under my face? Rats. Okay, I'm not doing so hot at this managing my screen tonight. But here's what I wrote. This sentence here is sort of how you'd want to sum up the problem. But, you know, what should the farmer build? The farmer should build 2 congruent 25 by 100 thirds foot corrals that share a 100 thirds foot wall. That's the wall they should share, not the 25-foot wall. Okay, anyway, I'm killing you. It's an hour and 3 minutes. I know all these videos seem to break the hour mark, but that's a good thing, right? Maybe this will be the one where you guys realize how much work I put in and actually say thank you to me. That would be cool. Anyway, what's on the next page? Please say nothing. Oh God, no, I don't want to do more. I didn't actually assign these, right? No, I took these away. Rectangles formed with blah, blah, blah. Rectangles formed with the base on the x-axis. The top corner is on the function of. What are we doing? Find the largest possible area of each object. I don't know. I'll show you guys these, I guess. If you want to ask me about them, you can. But these weren't on your homework, so I'm not going to do them. Well, there's only 2 anyway. With one corner at the origin and the other on the line. Da da da. Find the largest possible area of each object. Oh, because it goes down. I don't know. These are interesting, but whatever. Good night. Let's go to bed. Good night, everybody.